This is Dr.S. Prasanna, Assistant Professor of Mathematics in Pingil Government College for Women, Warangal. This video lesson is to BSc Final Year Mathematics in Sem 5 CBCS system. The paper is Linear Algebra. In the previous class, we have seen what is a column space, and we have gone through the definition of column space and some differences between null A and column A. And also we have solved some problems based on column space of that matrix, and under Roman 1 we have, that means the first model. In first model we have solved two problems yesterday in the previous video lesson. Now let us move on to the next problem in the same model, and the problem goes like this. Find a matrix A such that W is equal to column A, where W is equal to set consisting of the column vector with the entries B minus C, 2B plus C plus D, 5C minus D, D, where B comma C comma D are real numbers. So the set W is consisting of column vectors of such form, and we are asked to find the matrix A, and that matrix A is in such a way that W, this set W, is equal to the column space of that matrix A. That means W is equal to column A. And how we can find that matrix A, let us see now. We are given with the set W, and let us consider it first. W is given as the set consisting of the column vectors of the form B minus C, 2B plus C plus D, 5C minus D, D. Even though there are so many variables taken at a time, but in each entry, on the whole, it should be considered as a 4 by 1 column vector, as there are 4 rows but single column. So where in this the variables B, C, D are real numbers, are taken from the set R. So now W can be rewritten as changed as taking B common, C common, D common. The three variables are taken common separately, and to be multiplied as scalar multiples to some vectors, 4 by 1 vectors. Let us see how it can be done. So W is equal to set such that B times 1, 2, 0, 0 is the first column vector that is multiplied to B, because B, when we take B common in the arbitrary element of W, the coefficients of B in the 4 entries can be seen as 1, 2, 0, 0, as there is no B term in the third entry and fourth entry of the element of W. We can say that B is a scalar multiple of the column vector of 4 by 1 column vector with the entries 1, 2, 0, 0. Now take the next variable, that is C common. Then in the same manner, taking C common, we can see the column vector multiplied to C as minus 1, 1, 5, 0. Here we should understand that minus 1, 1, 5, 0 are the coefficients of C in the given, in the arbitrary element of W. So in the same manner, taking D common, we can get another column vector, 4 by 1 column vector, as which has the scalar multiple D, and that column vector is 0, 1, minus 1, 1. Here we can understand that D has the coefficients 0, 1, minus 1, 1 in the arbitrary element of W, in the definition of W. Now here B, C, D are real numbers, means B comma C comma D belongs to capital R. And what we got here is nothing but the linear combination of three vectors with the scalar multiples B comma C comma D. So this is the this denotes the linear combination of vectors, and those vectors are fixed, but the scalar multiples vary with the and with the numbers taken from the real number set of real numbers. So W can now be defined as the set of all linear combinations of the vectors 1 2 0 0 is one vector, minus 1 1 5 0 is the second vector, 0 1 minus 1 1 is the third vector. So now W can be written as span of these three vectors, because we know that recall the word span is nothing but the set of all linear combinations of the vectors or of some vectors, and whatever be those vectors, span contains those vectors as elements as the in a set. So W is equal to span of these three vectors 1 2 0 0 comma minus 1 1 5 0 comma 0 1 minus 1 1. These are the elements of the set span. Now let us take these three vectors, column vectors, which are 4 by 1 column vectors, which are the elements of span, the set span, as columns of the matrix A. Then we can write capital A is equal to 1 2 0 0 is the first column in the matrix A, minus 1 1 5 0 is the second column in the matrix A, 0 1 minus 1 1 is the third column in the matrix A. So then W can be written as column A. That is, W is nothing but the set of all linear combinations of columns of A. So that is how W can be represented as the set of all linear combinations of the columns of this particular matrix A. So the W is equal to column A for this matrix A. So now we can take this matrix as the required matrix in this problem. So capital A is equal to 1 2 0 0 minus 1 1 5 0 0 1 minus 1 1 as the three column which has these elements as three columns is the required matrix A in this problem. So what we have done is considered the set W, then rewritten it into set of linear combinations where B, C, D are the scalar multiples, and we got three vectors, and those three vectors we have taken in the set span, and those three vectors we have considered as the columns of a particular matrix, which is namely capital A, and this is such a way that W is equal to column A. So we can say that W is equal to column A for this matrix A. So this is the required matrix in this problem. So now let us move on to the next model, that is we will be given a matrix A, and we are asked to find the column space of a matrix. If the column space of a matrix is subspace of Rk, then what is that value of K? And similarly, the null space of that given matrix will be subspace of Rk, then what should be that value of K? This is the model in the Roman 2. And let us see the first problem in Roman 2 now. Let capital A is equal to 7. I will read the columns column wise. So it is 7 minus 2 0 minus 5 minus 2 0 minus 5 7 0 5 7 minus 2. These are the three columns in the given matrix A. Now we are asked to find if the column space of A, that means if the column space of matrix A is a subspace of Rk, what is K? And what is the value of K? They are asking us to find. And there is a second bit, if the null space of the matrix A is a subspace of Rk, what should be the value of K? That is the second bit. So here we are given with provided with a matrix A, and we are asked to find the value of K when column space of A, that means see column A is a subspace of RK and null A is a subspace of RK, then what should be K? So this is our question. Now moving on to the solution, we should know some point to remark to do this problem, to solve this problem. So what is that remark? What is that point to be noted down, to solve this problem is like this. If A is an m by n matrix, then the column space of A, that is column A, is a subspace of Rm, where m is the number of rows in that matrix A. So if A is an m by n matrix, then the column space of A, that is column A, is a subspace of Rm, and the null space of A, which is denoted as null A, is a subspace of Rn, where Rn is the n-dimensional space, where n is taken from the number of columns of the given matrix A. So this is how the column space is subspace of Rm, where m is the number of rows in the given matrix, and null space of A, null space of that matrix A, null A denoted as null A, is a subspace of Rn, where n is the number of columns in that matrix A. So in the problem given, we have capital A is equal to, it is given with, it is having 3 columns and 4 rows. If I read them in column wise, it is 7 minus 2 0 minus 5 is the first column, and minus 2 0 minus 5 7 is the second column, 0 5 7 minus 2 is the third column. But that means there are 3 columns, but there are 4 rows. 7 minus 2 is 0 is the first row, minus 2 0 5 second row, 0 minus 5 7 third row, minus 5 7 minus 2 is the fourth row. That means A is a matrix of order 4 by 3. So if we compare this m by n to this 4 by 3, we can understand that the value of m in this problem is 4 and value of n in this problem is 3. So that is how the column space of the matrix A is a subspace of Rm implies that column A is a subspace of R4, because in this problem m is 4. So column A is a subspace of R4. That means the column space of A, if it is subspace of Rk, then K should be 4. So the first answer to the first bit is K is equal to 4. So the column space is a subspace of Rk if K is equal to 4. Similarly, we have another formula, null A is a subspace of Rn. So using that, here applying to this problem now, the null space of A is a subspace of Rn implies null A is a subspace of R3. That means why is it we are taking R3 here? Because by the formula, by the note above, null A is a subspace of Rn, where n denotes the number of columns in the matrix A, and here in this problem the number of columns in the matrix A are 3. So that is how null A is a subspace of R3. Null A is a subspace of R3 means the null space of, if we can say that if the null space of A, that is null A, is a subspace of Rk, then K should have the value 3. So that is how in the first bit the value of K we got is 4, and the value of K in the second bit is 3. So this is the model of this Roman 2 under the problems Roman and in 2. So there are some more problems in this. So first understand this problem, then we can do more. Let A is equal to 7 minus 2 0. So we are given with a 4 by 3 matrix and we are asked to find the column space. If the column space of A is a subspace of Rk, then what should be the value of K? And we are also asked that if the null space of A is a subspace of Rk, what should be the value of K? And here we have seen that it is if A is an m by n matrix, then the column space of A is a subspace of Rm and the null space of A, that means null A, is a subspace of Rn. Even though I have given it as note point, but remember it as the formula for the problems under this Roman 2. So using this formula in applying to this problem, we can comparing the order of the matrix to m by n, we can understand m has the value 4 and n has the value 3. So the column space of the matrix A is a subspace of Rm. That means column A is a subspace of R4 and column A, if column A is a subspace of R4, then we can say that the value of K should be 4. So that is how the column space of A is a subspace of Rk implies K is equal to 4. So the first bit answer is K is equal to 4. And similarly, applying the second formula, second formula in the note point, we can understand that the null space of A is a subspace of Rn and here the value of n is the number of columns in the matrix A is 3. Therefore, null A is a subspace of R3. So the null space of A is a subspace of Rk. That means here the value of K should be 3. So that is how the number of rows and the number of columns of the matrix A are deciding the deciding whether the column A is subspace of Rk, Rm and the null space is a subspace of Rk where K is denotes the number of columns. So this is the second model. I have explained you again so 2 times. So do remember the problem and understand it well. Okay, with this problem I will stop the lesson for today because we have done a problem from previous model and a problem from another model. So if we want to go through this model again is to do some more problems, let us first practice. I want to give time for you to practice and get the problem understand well clear to you, then we can move on to the other problems, solve the other problems. So with this I close the class for today.